There are the three standard sort of cases that you get with projectile motion. The first one is when you have a horizontally launched projectile. In this case, your initial component of velocity is only in the x direction. There is no y component. So it's like saying that your initial y velocity is 0 meters per second. And the initial x velocity is 40 meters per second. Remembering that in x velocity, your horizontal component is not going to change. It's going to stay the same because we ignore factors like air resistance. What that means is that you can set up your equations very simply, and you're only going to have two equations. Basically, your distance equation, which is going to be half AYT squared, and you're going to have your horizontal component. So Sx, this is Sy, is going to be Vx0t. That you can have very simple cases where you can just find out how much time till the projectile strikes the ground and how far away it lands, talking about the range and how far it takes to get there, how long it takes to get there. So in this case, we've got 40 meters per second is our initial velocity, and we have a height initially of, I think it's 50 meters. So we're basically kicking something off the top of the cliff. So initially, we want to find out how much time passes. Our this would be using this equation here. But first we also want to include our initial position. I always tend to put our origin at 0. Some people put the origin up on top of the cliff and then they consider any movement below that as negative. Kind of depends on how you like to work. I tend to use the ground as the 0 point, which means that in this case we'll have to rewrite this equation in terms of the initial displacement, such as that. So if we write it as that, we want to find out how long until Sy is 0. So 0 is equal to 50 minus 9.8 on 2 t squared. So that means we're going to have t equaling a square root of 100 on 9.8, which is about 3.19 seconds, 3.2 seconds. Two significant figures. So then, if we want to find out how far the range of the projectile, we want to find out how far, we just substitute that back into the second equation here, which means S of x is equal to initial velocity, which is 40, times 3.2, which gives you a range of 128 meters. The second case that you'll commonly get is a projectile that's launched at an angle, and the range of the projectile, and of course how high it goes, depends entirely on that angle and the initial velocity. So what we want to find out is what is the time until it reaches the top of its flight. This is basically the maximum height. And it's sometimes called the midpoint because it's really the midpoint of the projectile. And this is where your velocity is 0. So if you're using your original equation, S of y equals velocity y 0 t plus a half a in the y direction t squared, then this would be when velocity y equals 0. We're actually going to use the derivative of that so that we can look at it in terms of Vy 0 plus AT. So this is exactly the same as the form in the standard form, which is V equals U plus AT. I'm going to try and use fairly consistent writing and consistent units so that we don't get mixed up with the standard form, and you always consider these things in 2 dimensions. So, finding out what the time until the projectile is at that maximum height. We know that's going to be 0, and we know our initial y velocity. Or do we? We know our initial velocity, we don't know the initial y velocity, but we do know the angle. So let's first figure out what are the x and y components of the velocity. So velocity y is going to be 40 times sine of what's the angle? 35. And in the x direction, it's going to be 40 cos 35. Remember, this follows from your velocity component here. That's your velocity v0, and this is your angle 35, which means that your Vy is over here, which is the sine, and your Vx is over here, which is your cos. So let's put our Vy in. We know at this point it's going to be 0. That's Vy max there, sorry. And this is going to be 40 sine 35 plus 9.8. That's actually going to be minus 9.8, remember, because it's in the negative direction, and then there's t. So what is that time? T is going to be minus 40 sine 35 over minus 9.8, which gives you 2.3 seconds. So how high does it rise? Well, now that we know the time, we can actually substitute this time back into our initial equation and find out how high it rises. So Sy is equal to 40 sine 35 times 2.3 plus half of negative 9.8 times 2.3 squared. You work that out and it becomes 27 meters. So it rises up to 27 meters at 2.3 seconds. How much time till it passes? How much time passes till the projectile reaches the ground? Well, it starts off at the ground. So it basically goes to its maximum height, the midpoint of the projectile's trajectory, and then goes to the opposite side of the ground, over here. And that just basically means that if you times your time by 2, then you get how much time passes. I'm going to put that as T max, which is 2.3 times 2, which is 4.6. This was actually 2.33, so this actually turns out to be 2.47 seconds. And that's important because you want to find out how far away. So if you're trying to find out the range, you now go to your x direction, where you use your x component of velocity and T max to find out how big your range is. So 40 times cos of 35 times 4.7, which gives you a maximum range of about 150 meters to two significant figures. It's actually about 153. The last case is a combination of both of those cases. So it's a projectile launched at an angle from an initial height. I'm going to set that height to 50 meters, just like in the initial case. So how much time passes till the projectile is at the top of its flight? Again, we're looking at the half point. So we're going to use that initial equation. Sy is equal to S0 plus Vy0 times time plus half a in the y direction, t squared. And substituting in your values, we're going to put in 50 plus 40 sine 35 times t minus 4.9 t squared equal to Sy. That's our initial equation. To get that time till the projectile's at the top of the flight, remember the top of the flight is when Vy is equal to 0. So it's actually going to be exactly the same as the previous question, which was when you had the derivative of this equation. So you had Vy equaling Vy0 minus 9.8t, where t then ended up being 2.3 seconds. So that was 2.3 seconds to get to the maximum height. How high does the projectile rise? Well, again, we did that in the previous question. We found that it rose an extra 27 meters. So that's basically the same as saying, well, let's see, we want to find out what is the position there. Sy is going to be 50 plus 40 times sine 35 times 2.3 minus 4.9 times 2.3 squared. So that's substituting that. You have your original 27 plus the 50 that it started off with, so 77 meters high. How much time till the projectile strikes the ground? This is where it gets slightly complicated, because now we actually have to use that first equation but solve it. So we have to say, we want to find out what is this point here, which is when Sy is equal to 0, and what is the time at that point. So let's put Sy equal to 0. 0 is equal to 50 plus 40 sine 35 t minus 4.9 t squared. So if you look at that, it's basically a quadratic equation. What you need to solve it is the roots of that quadratic equation. So I'm going to put them in C, B, and A and remind you of that quadratic formula. So T is going to equal minus B plus or minus square root of B squared minus 4AC all over 2A. We substitute that in, we get minus 40 sine 35 plus or minus the square root of 40 sine 35 all squared minus 4 times 4.9, remembering that that's negative, so that's going to make a positive there, times 50. All divided by 2a, which is basically minus 9.8. So I'm going to evaluate what minus 40 sine 35 is, and it's about 22.9. But I'm going to keep that in the calculator so I can use it further on, just so that you figure out how this goes. So we've got 22.9 here, all squared, plus 980 when you all put all that out, and minus 9.8. One more line, minus 22.9 plus or minus the square root of 1506 all over minus 9.8, and then plus or minus 38.8. Remembering that you're always going to have two roots for this quadratic equation. So the two roots turn out to be minus 1.6 and positive 6.4 seconds. Well, what that actually means is that your previous root is over here. This is the minus 1.6, and the time that actually takes is 6.3 over here. That's your second root. Those are the two roots of the equations. So we're going to use that second root here to work out how far away the projectile lands from its starting point. And that's very simple because now we're just using the horizontal point, which is going to use your Vx0 times that time that we found there. Vx0 is 40 times cos of 35, and we're going to times it by 6.4, which gives us a value of 20.6, no, not 20.6, 206, that's much better, 206 meters. So you can see that there are three different cases for this type of projectile motion, and they're solved very, very similarly. You need to use all of these different types of equations, and the ones that you've got to remember are basically those ones that you would have in the y direction. So in the y direction, you have your Vy is equal to Vy0 plus AT. And Sy is equal to, I always put in the S0 just in case you have an initial displacement. If you don't, then that's 0 and it just disappears. Vy0t plus a half AT squared. And then you can also use it if you want to. The Vy squared is equal to Vy0 squared plus 2ASy. In the x direction, because you don't have any components of acceleration, you just basically have your velocity in the x direction is just your initial velocity, which means that your displacement in the x direction is just the initial velocity times time. And you can also use the v squared one if you want as well. So really, these are the equations that you're going to use, those two, and this one here. Remember them, write them down, learn how to use them.